In this segment, I want to formally introduce the Boolean retrieval model and then also mention the kind of extended Boolean models that are conventionally used in commercial Boolean information retrieval systems. So Boolean queries are a system for specifying information needs where you're able to get an exact match in terms of satisfying the actual Boolean expression. Though again, as I commented earlier, that may or may not be actually a good Boolean expression for satisfying the user's information need. So when in information retrieval we talk about an information retrieval model, that means an underlying mathematical formalism for the information retrieval operation. So one example of an information retrieval model is the Boolean retrieval model, and in it what we say is the underlying mathematical model is the conventional space of Boolean expressions, and so you're allowed to ask for a term and then more complex expressions that are then Boolean combinations of terms. So you can ask for term and term, term or term, not term, term and not term, and progressively more complex expressions. So in this model, each document is viewed as a set of words, and a document precisely either matches the Boolean expression or doesn't match the Boolean expression, just as we saw in the earlier example with the term document matrix. This is perhaps the simplest model to build an IR system on, and in some sense is not normally the model that's used in the modern world, but it's a perfectly good place to start because the same data structures are used and the extra stuff that we normally now use for things like ranking can be overlain on the same basic foundation. So let's spend a bit of time just looking at the details of the Boolean retrieval model first. And also, I do want to mention that even though these days we're used to the ranked retrieval of search engines, this is actually a very important model, both for historical users and even some current users. So Boolean retrieval was the primary commercial retrieval tool for 3 decades, from the early beginnings of information retrieval in the 60s through the 90s. Although academic research on information retrieval started advocating ranked retrieval models in the 70s and 80s, really that hadn't penetrated the commercial information retrieval world until the web broke loose in the 1990s. But there are still also many current search systems that are still Boolean retrieval systems. So most likely the search system in your email, in your school's library catalog, or perhaps in your desktop computer such as the Mac OS X Spotlight, that those are all still Boolean retrieval systems. Let me show one example of an extended Boolean retrieval model, and this example is drawn from Westlaw. So Westlaw is the largest commercial search service in terms of paying subscribers, and is used in the legal profession for looking up case documents and related laws and related things. Now, Westlaw has gradually evolved over the years. It started in 1975, ranking was added in 1992, and they've got a new federated search model from 2010, and it's grown in size. It's now got tens of terabytes of data and large numbers of users, but it started off as a Boolean system, and an interesting thing is that a large percentage of the users still use Boolean queries. And I think there's something in that in the law profession, that lawyers like the precision of specifying their own Boolean queries, and there's been also then a long tradition in law schools of teaching people the language of the Boolean queries of the Westlaw system, so there's a lot of built-up user familiarity. But let's look at an example of the kind of query you get, and this is a little bit interesting because this shows in the kind of expert search scenario of something like legal search that you tend to get much longer and more precise queries than you're probably used to from web search. Okay, let's look at an example. So here we're imagining an information need for Westlaw. What is the statute of limitations in cases involving the Federal Tort Claims Act? And this is how it might be translated into a Westlaw query. Now, the Westlaw extended Boolean query language has some different conventions to what you're probably used to from web search. In particular, when you have two words next to each other like this, with just a space in between them, that means or in the Westlaw language, not and. But then for the other things that are being joined together, what we're seeing is some of the operators in the Westlaw language. So as well as having or and ands, it has a wide range of relational operators which specify that words co-occur within a certain distance. So here we have the /3 within 3 words, or you can also use structural units such as saying within the same sentence. And then finally, what we have here with this exclamation mark is how it specifies a wildcard at the end of the word. So this will match limit, limited, limitations, or anything like that. And so then the person is specifying that you have to have either statute or action occurring near to limit, which is in the same sentence as federal, which is occurring close to tort, which is occurring close to claim. So it's a detailed, precise query trying to match all of the elements of this information need. Here's one more example. So this time the information need is requirements for disabled people to be able to access a workplace. And so we see some of the same things, the wildcard. This is within the same paragraph, within the same sentence. And then here again we're getting this disjunction appearing, which is also then being disjoined here. Okay, so that should give you a flavor of the rather different kinds of queries that are seen as typical Westlaw queries. And as I already remarked, many professional searchers really still like this kind of extended Boolean search because they're very precisely able to specify things like how the wildcarding works or exactly how close together words have to be. And these are facilities that you can't control for yourself in the same way in most typical web search engine query languages. On the other hand, that doesn't actually mean that searchers get better results when using these kind of precise query languages. There are actually some interesting user studies done by Westlaw's own scientists showing that in many cases that people's ability to formulate good Boolean queries is worse than the quality of results that you get by more automated means of ranking results with more web-style ranked retrieval engines. Okay, so now let's get back to the Boolean retrieval model in its just pure Boolean form, and we'll consider how we can do some other kinds of queries as well as the AND query, or at any rate I'll encourage you to think about it. So suppose we don't want to ask Brutus and Caesar, but maybe we want to ask Brutus and not Caesar, or Brutus or not Caesar. So something that would be great for you guys to think about is, can we do these kind of queries with a merge algorithm? Can we merge in time proportional to the sum of the length of the postings lists of the two terms? Or if not, what kind of complexity can we do these operations in? And if you've gone through those cases, well then you might consider, what if we have an arbitrary Boolean formula like this? In those cases, can we merge in linear time or not? And again, if so, linear in what? Could we imagine doing better than the merge algorithm to solve these problems? So those would be kind of good things for you guys to think through on your own time. But let me move now to query optimization. And this is, if you have a complex query with various words in it, think again of those Westlaw queries, we can try and work out what's the best way of algorithmically going about satisfying that query. So consider a query that is an AND of n terms. So what we want to do is somehow or other get each term's postings and then AND them together. So here we have the postings list for the 3 terms, and we want to be sticking them together. Well, what heuristic should we use to minimize the amount of work that we do? Well, I hope it's fairly straightforward to see that what we should do is start with the term that has the lowest document frequency that occurs in the fewest documents, here Calpurnia. Because for a pure AND query, we know this postings list is the maximal set of results that we could possibly need to return. And so what we then have to do is go through the postings lists for the other words and then filter out ones that don't also occur in their postings lists. So we would next look at the postings list for Brutus, and we could chug through it and see that 13 isn't on it, and we've gotten rid of this possibility, and so 16 is our remaining postings list. And so then we would move on to the postings list for Caesar and chug through it and find 16, and so we're going to return as our answer just 16. And so this operation was clearly made more efficient, both in terms of time and in terms of the storage space of a postings list in memory, by starting with the smallest postings list. And I hope that also then made clear why it's a really good idea to keep the document frequency of each word together with the word in the dictionary, because that lets us do a very quick in-memory lookup to work out what's the best query optimization strategy. Well, suppose now that we have a more general sort of query. So suppose, for example, we're looking at this query, madding or crowd and ignoble or strife. Well, we can certainly now easily get the document frequency for each term, but we have to do something a little bit more complex to optimize this query. Well, what we can see is that for each of these pairs of disjoint terms, we'll then be unioning two postings lists. So that'll be able to make a list that is at least potentially bigger than the postings lists of either of the individual terms. So we could estimate the size of these subterms by taking the sum of the document frequencies of each disjunct, and that will give us a conservative upper bound on how long the resulting postings list could be. And then if we then have an AND operation occurring between these disjunctions, we can then use the same heuristic as before. We can process an increasing order of OR sizes. Here's an exercise you can do just while you're listening to these slides. So here's our query where we have a conjunction of three disjuncts, and here's just the relevant subset of the dictionary of the terms and their frequency. And what you should do is work out which two terms should we process first. In general, working through the details of these merge operations is a really good thing for you to think about. And so here are a few more examples. So if the query is friends and Romans and not countrymen, well then how do we use the frequency of countrymen in our query optimization method? Well, what if we go to even more general things like an arbitrary Boolean query? Can we always guarantee execution time linear in the total posting size? You might want to think about that and think about, in particular, this case where a query term appears only once in the query, and see if you can work out what kind of bounds you can put on the total time to do a merge. At a more practical level, you could also just start thinking about how search interfaces work and what's useful or not to people. So here's actually a teeny little search engine that lets you search the works of Shakespeare. So a useful exercise would be to just take a look at it, do a few searches for things in Shakespeare plays, and see if you can think of some things that would be useful if this search engine could do better. Okay, so we've introduced the Boolean retrieval model, which is the historically most important retrieval model, but also a very important basis for understanding how modern retrieval systems work.